In the last video, you saw that you can convert between polar coordinates and rectangular coordinates. In this video, we're going to do something very, very similar, and you can convert equations as well. So a polar equation is an equation whose variables are r and theta instead. Now, here are a couple examples. Again, there's many, many examples, obviously. So r equals 5 over cosine theta plus sine theta, r equals 6 cosecant theta, etc. So these are just a couple examples where, again, you're using r and theta rather than x's and y's. And just like with the points, you actually can convert back and forth between rectangular equations and polar equations. So let's look at a few examples there. All right, so we're going to convert each rectangular equation to a polar equation that expresses r in terms of theta. So what does that part mean? If you see expresses r in terms of theta, it just means to solve for r. So we want it to be r equals as our final results, just like the examples you just saw. All right, so for the first one, we're going to do x plus y equals 5. And again, these ones are pretty straightforward. So you want to remember that x is equal to r cosine theta and y is equal to r sine theta. So we saw that conversion in the last video. So we can go ahead and plug those in. So x, becomes r cosine theta, y becomes r sine theta. Now, if we could simplify, you would want to do any cleaning up. The only thing is we do want to solve for r. I can't actually add these together, right? Because sine and cosine are two different trig functions, so I can't just combine them. What I can do, though, is I can factor the r out. And this is actually a really good trick if you need to get a variable by itself, and yet you can't figure out how on earth could I add or subtract these. It doesn't work. Factor it out. Once I factor it out, I can divide both sides by cosine theta plus sine theta. And you can actually see that we got that first example that I just gave you on the other page. Okay, so your original equation was x plus y equals 5, and the polar equation is r equals 5 over cosine theta plus sine theta. So we're going to do a second one here. This one's a little bit more complicated, but it's going to work the same way. We're going to replace our x's and y's. So for x, we have r cosine theta. And then for y, you have r sine theta. Now I am going to multiply these out. I do have to square it here. If you can do this in your head, go ahead. I like to write it out. So here you're going to go ahead and FOIL. So we start with r cosine theta times r cosine theta. And what you get is r squared, right? R times r is r squared, and cosine squared theta. And then on the outside, you have minus 1 times r cosine theta. On the inside, minus 1 times r cosine theta. Minus 1 multiplied is going to be positive 1. Here, I squared this as well. I didn't write this one out, but if you write it out, it's r sine theta, r sine theta. So r times r is r squared, and then sine and sine is sine squared. So it's r squared sine theta, and then finally equals 1. I'm going to go ahead and clean these things up. I'm going to put my squares together here. I can move it around because they're just addition. I'm going to combine my like terms. So this is minus 2r cosine theta plus 1 equals 1. I'm going to subtract this 1 from both sides, and it's going to cancel it out. Just be careful, it does cancel on both sides, but you do need something on the other side of the equation. So there'd be a 0 there. Now, this is looking familiar, sine squared and cosine squared. It's almost the Pythagorean theorem. So what I'm going to do is factor out that r squared, and then I'll have sine squared theta plus cosine squared theta. And then I know that this becomes just 1. R squared times 1 is just r squared. So now I have r squared minus 2r cosine theta equals 1. Getting a little bit more cleaned up here finally. Oops, where did I get the 1 from? Oh, made a mistake. Sorry, that was a 0. Again, I need you guys live so you can tell me, hey, professor, you made a mistake. I apologize. The 1, I think I was just thinking of this, but obviously this is a 0 here. So rewrite that as 0. That makes much more sense. Next, I do need to keep solving here. Because I have a square, you want to think about quadratics. Usually, in most cases, we like that right side to be 0. So I'm going to try to leave that. I'm going to instead factor out an r here. So then I have r minus 2 cosine theta equals 0. And then now I have 2 factors, so I can set each factor equal to 0. So I do have 2 solutions, r equals 0 and r equals 2 times cosine theta, excuse me. However, note, in this case, right, if theta is equal to pi over 2, then r would be 0 because cosine of pi over 2 is 0. So I don't need to really have this extra equation. It's already included here as theta runs through all the values. So sometimes you may have two equations that work, but here r equals 0 is just redundant because I already have it here. When theta happens to be 90 degrees, pi over 2, then cosine is 0. So you get that r equals 0 answer as part of this equation already. So I really only need one final answer here, and that is r equals 2 cosine theta. So actually this format is actually much simpler, whereas the last one I kind of made it harder. Here I think he went from something that was pretty complicated down to a little bit of a simpler formula. Now we can also go the other direction, and just like before, this tends to be the harder ones. So we're going to go from polar equations to rectangular equations. And here it's a little bit more like a puzzle. So there's 4 different equations that you may use. Whereas in our last example, find it. In our last example, when we're going from rectangular to polar, you're always using these 2, and it's pretty straightforward. Just plug in and simplify as much as you can. When you're going from polar back to rectangular, here it's a little bit harder. So there's always kind of one hard version, I feel like, for this section of when you go back and forth. You could use the fact that r squared equals x squared plus y squared. That's helpful. You can also use the fact that x equals r cosine. Oops. Let's try that again. X equals r cosine theta, and that y equals r sine theta. So that can be helpful. And then we also have the fact that tangent theta equals y over x. So any one of these may be helpful in converting. All right, and let's look at a couple of examples here. So we're going to convert each polar equation to a rectangular equation in x and y. So let's start with example A. R equals 5. Okay, there's really not too much to do here, right? I mean, there's nothing going on. If I look at all my equations, I guess I have a few different options, but the one that kind of stands out to me is this r squared, right? Because I want things in terms of x's and y's, and I see an r here. Whereas here I see an r, but I still see cosines. So this is the one that's saying, hey, this probably will work. So I'm gonna go ahead and do that. But it's supposed to be r squared, not just r. So if I square both sides, I end up with r squared equals 25. And then I can go ahead and substitute in now. X squared plus y squared equals 25. So we're done. So if you recognize this is actually a circle with radius 5 right around the origin. So this kind of makes sense because in the polar form, you're going 5 units out. And if you run through all the thetas, you're going in that circular motion. So here you have that circle with radius 5. This is B. My second equation is just theta equals pi over 4. And again, this one's a little bit tricky. If I kind of look at my options, this first one doesn't seem like it's going to be helpful at all. I see cosine theta, but then I also see r there too, and I'm trying to get rid of those. So I think my best bet is to use tangent theta. So what I can do here is I can take the tangent of both sides in this case. Now, pi over 4 is that 45-degree angle. Tangent of pi over 4 is one that we do know. It's the value of just 1. So we are able to simplify this. And then now you see that you have that tangent theta, and I can go ahead and use the right side. So this becomes y over x equals 1. I can multiply by x on both sides here. And I get y equals x as my final equation. So like I said, these ones are a little bit harder. I feel like they're much more puzzle-like, where you kind of have to look at the different options and see which one is going to fit best. All right, here's my next equation, r equals 3 cosecant theta. If I look at my options for conversion to x's and y's, I do see an r, but that cosecant, remember, is 1 over sine. So my brain is thinking, maybe I can use this in some way, right? So let's try manipulating this a little bit first. So this becomes 3 times 1 over sine theta, or we can just write this as 3 over sine theta. And if I multiply both sides by sine theta, I get that r times sine theta is equal to 3. Well, r sine theta is y. So I can go ahead and substitute this in. And I get the equation y equals 3 here. So we have that nice horizontal line. I'm going to do one more. I think I can fit it all on one page. Let's see. Okay, so we're going to do r equals -6 cosine theta. Now this one's a hard one. This one's a bit tricky. So if I go up here, the one that jumps out to me is this one, right? R cosine theta. I see a cosine theta here, but I don't have the r feature. So what I'm thinking is if I multiply by r there, then I could have that r cosine theta and make it an x. But I can't just do it on one side, I have to do it on both. So I'm going to multiply both sides by r in this case. So we have r times r equals -6 cosine theta times r. So r times r is r squared. And I'm just going to move the r in front here to make it look a little bit nicer. So now I have that r squared is equal to -6. And I can make this now x, right? Because r cosine theta, we said, was x. Now, not quite done. I still have this r squared on the left, but r squared is equal to x squared plus y squared. So I can make a second substitution there. And then I can go ahead and just maybe clean this up a little bit. So I'm going to bring my 6x to the other side. I'm going to go ahead and add 6x to both sides. Now, there's different ways that you could write this final answer. So I'll show you one way. So x squared plus 6x plus y squared equals 0. That is one way that you could write the final answer. What your book has you do is it does have you complete the square there and take it a little bit further. So that's another thing that you could do is you could complete the square. So I will say that, you know, this is a fine answer. There's nothing wrong with it. It just depends on what form you want your final answer to be in. So for your book here, it does ask you to kind of keep going and complete the square in that case. So we can run through those steps as well together, and then that way you'll have that final answer too. So continuing on, I want you to notice here that we have an x squared and a y squared, but the middle term is just x. So it's not xy, which is a little bit different. It's just an x. So what we can do is we can complete the square for the x piece here. So I'm really focusing on the x piece for a second. And I'm going to notice here that my b is equal to 6. So in completing the square, what we do is we take 1/2 of b. So in this case, half of 6, which is 3. And then what you do is you square that value. And in this case, we would get 9. So what I do is I would go ahead and add 9 to this problem. But I can't just do it with the x part. I have to do it on both sides, right? To make it even. So 0 plus 9 here. And then what happens is this left side factors. And the way it factors is it always factors as x. Well, here it's x for your variable. So x, and then whatever half of b is. Half of b was 3, so that's where the plus 3 comes from, and then it's squared. So this is actually a pretty common way to write an equation of a circle as well. So that's why for this example in your book, they do actually like you to convert it over. But again, there's nothing necessarily wrong with this answer. It just depends on the format that we want it in. So this is a way that we also write the formula for a circle. And just kind of a little quick review there of the completing the square technique. So this would be the final answer for how to write the original equation that we had here, our polar equation, into the rectangular form with x's and y's.